Hello, my name is Adam Fast. I'm a master's student in plant science with a focus in agronomy at the University of Alberta in conjunction with Agriculture and Agri-Food Canada in Lethbridge. And today I'm going to be talking to you about my research. It is entitled Integrating Enhanced Efficiency Fertilizers and Nitrogen Rates to Improve Canada Western Red Spring Wheat Production in the Canadian Prairies. So I'll give you a bit of an overview for my presentation today. In a bit of an introduction, we'll go over nitrogen and Canada Western Red Spring Wheat, nitrogen cycle and urea fertilizer loss. We'll go over enhanced efficiency fertilizers, and then we'll do an overview of my experiment looking at location, experimental plots, some preliminary results, a quick note on greenhouse gas emissions, and then some conclusions, references, and acknowledgements. Firstly, I'd like to reinforce the importance of nitrogen that I'm sure we're all aware of. It's often the most limiting crop nutrient, and industrialized food production is dependent on it, and industrialized fertilizer production. And Canada Western Red Spring Wheat is no exception to this. CWRS is Western Canada's largest wheat class. In 2021, about 6.7 million hectares were planted in Canada, and about 2.3 million of those were planted in Alberta alone. And nitrogen in CWRS is conventionally applied as granular urea fertilizer at planting. Here is a picture of the nitrogen cycle as it pertains to crop production. All of the green plus signs are additions of soil nitrogen, and all the red minus signs are losses of soil nitrogen. And the three most common methods of nitrogen loss that are pertinent to enhanced efficiency fertilizers are ammonia volatilization, nitrate leaching, and denitrification. Enhanced efficiency fertilizers are specialized coatings, chemicals, and compounds that have been added to conventional fertilizers to do one of two things, which is improve plant nutrient uptake and or reduce nutrient loss to the environment. And these functions are all relative to the conventional alternatives that a EEF is applied to, in this case, urea. There are three main types of enhanced efficiency fertilizers when we're talking about nitrogen. The first being slow or controlled release fertilizers, SRFs, and these fertilizers aim to release soluble nitrogen at a slower rate to better match the crop's demand. An example of this seen in Western Canada is polymer-coated urea or environmentally smart nitrogen, ESN. The next class is urease inhibitors, UIs. These guys, they temporarily inhibit the urease enzyme. An example of that is NBPT found in agrotane. And next up there's nitrification inhibitors, NIs, and these temporarily inhibit nitrifying bacteria populations. So that's found in nitropyrin, the active ingredient in Entrench. And then there's also dual inhibitor products which contain both urease and nitrification inhibitors. An example of that is SuperU. This slide shows three pictures. Urea on the left is our conventional method of CWRS fertilization. We have SuperU in the middle, which is a dual inhibitor, and then ESN, which is a slow/controlled release fertilizer on the right. This slide simply shows the visual differences that typically accompany these different enhanced efficiency fertilizers. This is a diagram depicting the typical fate of unprotected urea fertilizer when applied to field crops, and how the three most common types of enhanced efficiency fertilizers function. So, firstly, upon soil contact, urea will first hydrolyze into ammonium ions, and if these ions are near the soil surface, they can be subject to ammonia volatilization loss. After this, these ammonium ions can be converted to nitrate anions through nitrification, and due to their high solubility in water and negative charge, these nitrate anions can be lost to runoff, leaching, or be used in microbial respiration during denitrification. So slow release fertilizers, they're designed to slow down this entire process where soluble nitrogen released from the granules will better match the demand of the crop and be taken up quickly. Urease inhibitors, they're designed to slow the process of urea hydrolysis, which affords the fertilizer granules a larger time to be incorporated into the soil and broken down to ammonium cations, which can be adsorbed to exchangeable sites in the soil. And lastly, nitrification inhibitors suppress nitrifying bacteria populations, and this happens temporarily, and it allows the soil inorganic nitrogen to remain in the ammonium form rather than the nitrate form. And being in the ammonium form, they have a greater chance of being adsorbed safely to exchangeable sites and not be lost to leaching, runoff, or denitrification. So now I'll talk to you about my research. It's a two-factored experiment. We're growing AAC viewfield plots, like the picture on the right shows, and we're subjecting it to nitrogen forms and nitrogen rates. So we're looking at 6 different nitrogen forms: agrotane, a urease inhibitor; Super-U, a dual inhibitor; Entrench, a nitrification inhibitor; ESN, a slow-release fertilizer; a new chemical out of Europe, NBBT DMPSA, which is also a dual inhibitor; and then typical untreated urea at 4 nitrogen rates: 60, 120, 180, and 240 kilograms of nitrogen per hectare, side or mid-row banded. To put succinctly, this experiment involves side banding 6 different nitrogen fertilizers at 4 different nitrogen rates. It's a factorial arrangement of a complete block design with 4 replicates, and we also have 0 null control plots, but they're not used in my analysis. There are 6 locations of this experiment across Alberta and Saskatchewan. There's one in Lethbridge, one in Vermilion, one in Edmonton, and one in Beaver Lodge in Alberta. There was one in 2019 at Barhead, Alberta. However, that changed when Alberta Ag went defunct. And then there's also a location in Indian Head and Scott, Saskatchewan. Here's an aerial picture of my experiment at the Edmonton site. My experiment is here on the top right of the screen, laid out in a bit of a different fashion just to fit field configurations, but this just simply illustrates the large degree and the large scale of these agronomic trials. So the plots for this experiment, they varied by location and seeder configuration. However, in Lethbridge, 10-meter plots were sown with a no-till air drill using Conservapac openers, and the plots were grown according to conventional agronomic practices, and typical agronomic data was collected throughout the growing season, and afterwards, after harvest, protein content and yield were determined. So some preliminary results that are overall averaged across the first 3 years of this experiment are that nitrogen form did not affect yield or protein content, while nitrogen rate did. The graph on the left shows yield as a function of nitrogen rate, and the nitrogen rate of 180 kilograms per hectare significantly improved yield over 60 kilograms of nitrogen per hectare, while 120 and 240 produced similar results to each group. And the graph on the right, showing protein content as a function of nitrogen rate, showed significantly increased protein content at each increasing nitrogen rate. These results are preliminary so far, and they will be subject to change with the full data set coming in the coming years. I would like to make a quick note on greenhouse gas emissions. There is another component of this experiment that examines GHG emissions from these plots, and it has been observed that some of these enhanced efficiency fertilizers are reducing nitrous oxide emissions relative to urea. This is not a part of my thesis, however, but I thought it'd be interesting to mention. To conclude, So far, the amount of nitrogen applied has had a larger effect on yield parameters in CWRS than the type of nitrogen used. The field conditions that these experimental plots have been exposed to did not widely promote nitrogen loss. Nitrogen rates of 120 kilograms of nitrogen per hectare provided higher yields and exceeded protein minimums in CWRS while having lower input costs compared to higher nitrogen rates. Growers who suspect nitrogen loss and incorporate EEFs in their CWRS production are not going to be subject to reduced yield parameters and may benefit from modest increases and/or reductions in GHGs. And further genotype-specific studies are needed in the major crop-producing regions of Western Canada to determine the applicabilities of enhanced efficiency fertilizers. Here's a slide showing my references and the images that I used in this presentation. And lastly, I'd like to thank all my collaborators and the funders that funded this research, as well as all the technical research and student staff who had anything to do with the success of this experiment so far. I would also like to thank all of you for attending, and my email is acfast@ualberta.ca if you ever wanted to reach out or have any questions. Thank you.